Welcome back, students. So we were talking about yield criterions and two conditions, or actually there is one condition that any yield criterion must satisfy, is that it should not depend upon hydrostatic stresses. So that is something that we looked at or we realized last time. So the criterion should not be influenced by second thing that we noted was that if we want to arrive at such a criterion, then it should be some function of deviator stress. Okay, so with this understanding, let's look at how to get to one of those criterions, and it is One Message Criterion. Now you remember that if you want to get a principal stresses, then the principal stresses are given from this equation where I1, I2, I3 are invariants. And invariants, again, we discussed with respect to how to derive a criterion. There we discussed that the criterion should also be independent of axis. So it must be some function of the invariants. And invariants of a deviator stress. Okay, so this is how our equation looked like. For finding the principal stresses, the roots of this equation would give you the principal stresses where I1, I2, I3 are invariants. And one of these invariants, I2, looks like this. If you write it in general terms, it is like this. And if you write it in terms of principal stresses, this is how it looks like. And this particular invariant happens to be independent of coordinate axis. Actually, all of them would be, and this one is even more interesting. By the very definition, the invariant should be independent of invariant axis. Now, this is how our deviator stress looks like, sigma ij prime, where now we have taken away the hydrostatic stress from the diagonal component. So this is how it looks like. So let's call it sigma x prime. This becomes now. Let's try to find the second invariant for this deviator stress. And this is sigma x prime, sigma y prime, sigma z prime. Similarly, we can also write this in terms of principal stresses. Then it will become sigma 1 prime, sigma 2 prime, and sigma 3 prime. And in that case, your invariant for the stress deviator would be obtained from this equation. So this would give you the principal stresses for deviator stress, where J2 is the one that we are interested in. So J2 going from this previous equation would look like, would have this form, and I've already written the equation so that there is no error in when I'm writing it down. So J2 would look like this in terms of sigma x, y, z, or in terms of principal stresses, it would look like this. Where remember, sigma 1 prime would mean 2 sigma 1 minus sigma 2 minus sigma 3 by 3. Sigma 2 prime means 2 sigma 2 minus sigma 3 minus sigma 1 by 3. sigma 3 prime means 2 sigma 3 minus sigma 1 minus sigma 2 by 3. So if you take this as your, now this not if, but this is now your J2 or the second invariant of the deviator stress. And based on our understanding from the last class, it is this particular function is, this is a function of deviator stress, and it is a function of invariance of the deviator stress. And more, what's more is that if you expand it, you write sigma 1 prime and sigma 2 prime and sigma 3 prime in terms of sigma 1, 2, 3, then it translates into this form. And here you can clearly see now this form shows that it is clearly a function of shear stress. So it is a function of shear stress, satisfies the first condition. It is the function of a deviator stress, it satisfies the second condition, and it is a function of the invariance. So it satisfies the third condition. And therefore, this looks like a very good candidate for defining a yield criterion. In other words, we can write the one Mises criterion can now, based on this, can be written as, we can get rid of the factor here and we can write when this function reaches some critical value, let's call it C. So this C would be a constant. So when this function reaches some critical value, then this particular material which is in this stress state would yield. Now, if you take this as the definition of yielding, then you can see it is taking into account the overall stress state. It is taking into account only the shear stresses, as we expect that only shear stresses cause plastic deformation, and it is a function of deviator stress, and it is a function of the invariance of the deviator stress. So certainly it does define some mechanics which will describe the yielding of the material, and therefore this will be a very good criterion to define yielding. And now how to obtain, the next question is how to obtain this constant C. So this is a constant that we know. Okay, and let me, to be precise, so that we understand, when this function, which is on the left, so when F sigma reaches or exceeds critical value C, then the material starts to yield. Okay, so we have now a criterion, and it looks a lot more simple than we initially thought it would be. And now we are, what we need to do is find out the value of this constant C. So how do we find the value of constant C? For that, we know that this particular equation should be valid for all conditions, and that would mean it should also be valid for uniaxial tensile condition. Now, when we are talking about a uniaxial tensile condition, then we know that it can be represented by a Mohr circle like this. So this is a uniaxial tensile condition. And what happens in a uniaxial tensile condition? We have sigma 1 at the point of yielding. Sigma 1 is equal to y. Sigma 2 is equal to 0. Sigma 3 is equal to 0. So if we insert these values, sigma 1, sigma 2, sigma 3, then we will have the value of C in terms of y. So let's see how does it look like. And if you put it all together, then you would see that basically here sigma 1, all other terms goes to 0, only sigma 1 and remains non-zero, and it is y. So this is y square plus y square. So it is 2y square is equal to C, and therefore constant is equal to 2y square. On the other hand, we can also find this constant in terms of the shear strength. And for shearing, we know that this is a Mohr circle that represents the shearing condition. So this represents and under shearing, we know that sigma 1 is equal to plus k, sigma 3 is equal to minus k, and sigma 2 is equal to 0. So now when we put sigma 1 equal to plus k and sigma 3 equal to minus k and sigma 2 equal to 0, what we get is C is equal to 6k square. You can check that out. It will be a good exercise for you and a good hands-on experience if you do this on your own. It's a one-step process. So C is equal to 2y square in terms of yield strength, where y is yield strength of the given material and k is the shear strength of the material, which means that based on this criterion, we get a relation between y and k. And what is that relation? What we get is that y square, 2y square is equal to 6k square, or y is equal to root 3k. So if you have shear strength of the given of a material, you can find from that, you can find what should be the yield strength, or if you have the yield strength given, then we know that y over root 3 would be the shear strength of the material. So this is our One Message Criterion. So let me write it. And it would be written something like this. This would be the formal way to write this One Message Criterion. That this value should reach C or above for yielding to occur. Now here we have sigma 1, sigma 2, and sigma 3. And if you want to see how the sigma 1 varies with sigma 3 at the point of yielding. Okay, so we want, let's say we want to draw the locus of how the sigma 1, 2 are related at the point of yielding. Then what we can do is we can take one of these sigma 1, 2, 3 as a constant, let's say 0. Okay, so and now since we are taking one of them 0 and keeping it constant, therefore we are not following the convention of sigma 1, sigma 2, sigma 1 greater than sigma 2 greater than sigma 3. And therefore, let's not use the term sigma 1, 2, 3. Let's use the term sigma A, sigma B, and sigma C. Okay. And here, let's say for the condition sigma B equal to 0, how does the plot look like? Okay. So if you write, so all you have to do is in the sigma equation that we have over here in terms of sigma 1, 2, 3, you can see it is symmetric with respect to sigma 1, 2, 3, as long as it is in this form of the equation. Here, let's say that sigma, we will now convert it to sigma A, B, and C. So we will write it as So here we are taking this equation and converting 1, 2, 3 to ABC, and the constant is C, which we know is equal to either 2y square or equal to 6k square. Now here we are saying that we want to draw a locus at the point of yielding, and to simplify the equation, because it will be a three-dimensional equation, we will keep sigma b equal to 0, and therefore now we have two axes, sigma a and sigma c. So the equation would be in terms of sigma a square plus sigma c square minus sigma a sigma c equal to, and you would see in terms of y and k, it becomes y equal to y square or equal to 3k square. If you draw this, how it would look like. So it's an ellipse, remember. And the axes are, as I have said, one is sigma A and the other is sigma C. So these are still the principal stresses, only that we don't know which one is 1, which one is 2, and which one is 3. So we have named it as sigma A, B, and C. And now at this particular point, here what we have is sigma C is also equal to 0. So if you put it in this equation, then what you would find is that this value is equal to y. Similarly, this one will be equal to y. This one will be equal to minus y. So although the ellipse may not look symmetric, but you will have to take my word for it. And this is tilted at 45 degrees. So this is the line which is at x equal to y angle, meaning 45 degrees angle. And what we see is that if you go to these points, so here sigma A is greater than y. Here sigma C is greater than y. Here sigma A is less than minus y. Here sigma C is less than minus y. Here both of them are less than minus y. Here both of them are greater than plus y. So what it is showing is that the individual principal stresses can be higher than y. This plot, this ellipse, as long as you are inside it, then no yielding is taking place. So as long as the principal stresses, the stress state is such that the principal stresses lie within the circle, then no yielding is taking place. As you reach this circle, it is then that you are actually beginning to yield. And when you are above this circle ellipse, then or beyond this line, then the yielding has begun. So this hatched region, is no yielding. Okay, and over here it is everything beyond this is actually yielding. And the line describes the partition. So from no yielding to yielding. So if you were a looking at the uniaxial, so here it is, you are increasing the stress, and at this particular point, your stress has reached the strength of the material. So here yielding begins, and when you keep increasing the stress, then more and more deformation is taking place. And as long as you are below this, no yielding is taking place, you are in the elastic regime. But then now we are in a multi-axial stress state, and in this particular case, two-axial stress state. So as long as you are inside this circle, then you are not leading to any yielding, and beyond this, you are causing yielding. And what we see is that principal stresses even higher than the yield strength may not lead to yielding up to a certain value, of course, as you can see. So there is a possibility that the principal stresses may be higher than the yield strength of the material, but you are still not yielding given the stress state. Okay, so this is something that we looked at from the example, but now here we can clearly see with the help of the equation that we have derived for the criterion. Yeah, so now also I wanted to end this particular criterion. I would also like to give you the generalized equation, meaning so far we have looked at in terms of principal stresses. How would this equation look if we had a general stress state, meaning sigma xyz and tau xyz? So in that particular way, it will be written like this. So this is the generalized form of the one message equation. So in this particular section, we have looked at, we started from our requirements that there should not be, the criterion should not be influenced by hydrostatic stress, should be a function of deviatoric stress, should be a function of invariants. From there, we come to this J2, and therefore we can say that when J2 reaches certain value, it will start to yield, and we can, if we remove the factor, then this is what we are left with, the sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square equal to C. Then we moved on to find the value of C, and we found that C is equal to 2y square in terms of yield strength of the material, or equal to 6k square, where k is the shear strength of the material. Then we looked at the locus in two axes, sigma A and assuming sigma B is 0. This is how it looks like. And in fact, we also looked at the generalized form of the equation. This is how it would look like if we have the stresses in the general form. And now just the last point regarding the one misses, if you were to draw the surface in the 3 dimension where the yield begins, then it would be a surface, and that surface would actually look like a tube. So let me just draw this. So again, I will not use sigma 1, 2, 3. I would use sigma A, sigma B, and sigma C. And this would be tilted at a equiaxis angle from all the 3 axes. And the tube would be so this is what the equation that we have describes. This is the surface that you will get for the yield in the 3 principal axis directions. And the radius of this circle can be shown to be, sorry, not the circle, the cylinder. And this would be called the yield surface. So again, what it means is that as long as the principal stresses lie within this surface, then yielding does not take place. But if you are at the line, yielding just begins. And when you cross this line, then deformation is continuously taking place. Okay, so we will now move on to, so this is the von Mises criterion. Now let's move on to still another criterion. And the name of this criterion is Tresca, or max shear stress criterion. You remember we said that shear stresses are what causes the yielding. Or plastic deformation. So one of the criterion directly picks up from here and says that the yielding will occur when the largest shear stress will reach a critical value. when largest shear stress reaches a critical value. And if you remember one place, we showed that principal shear stresses can be expressed in terms of principal stresses. And of these three principal shear stresses, the one that is the maximum is sigma 1 minus sigma 3 by 2. So basically sigma 1 minus sigma 3 by 2 should reach some critical value. Or in other words, we can write it like this, that sigma 1 minus sigma 3 should reach some critical value C. This becomes our max shear stress criterion or the Tresca criterion. Now here again, we have a constant C. Therefore, what we want is to define the value of or find the value of C. So one of the conditions that we can utilize is again the uniaxial tensile condition. And we know that under uniaxial tensile condition, sigma 1 is equal to y, sigma 2 is equal to 0, sigma 3 is equal to 0. Therefore, when you put it over here, we get y minus 0 equal to c. And therefore, this value of c is equal to y. Now, like previous time, we will also try to find this constant in terms of the shear strength of the material. So we know that the pure shearing takes place then under. So this is the pure shearing condition, and this is the Morse circle that represents the pure shearing condition. Under this, we have sigma 1 is equal to y, sigma 3 equal to this should be k, sigma 3 equal to minus k, and sigma 2 is equal to 0. Therefore, what we have now is that k minus k is equal to c, or c is equal to 2k. Therefore, now we can write down the equation like this. This is what the Tresca criterion translates to. Sigma 1 minus sigma 3 is equal to 2k is equal to y. And this also gives us another relation between the yield strength and shear strength. So here we see that y is equal to 2k. On the other hand, there in the previous case, we had y equal to root 3k. So there is a slight difference, and that is dependent upon how we have derived the two equations. So now that we understand the other criterion, the Tresca criterion, let's move on to finding the locus of the yield points in terms of the principal stresses. So again, what we want is to derive this equation or to draw a profile or the locus in terms of the principal stresses. But again, we don't know which one is sigma 1 and 2 and 3. So we will write this in terms of sigma A, B, and C. So let's say this becomes your sigma A. This becomes your sigma C. Now, we will also draw a 45-degree line, that is x equal to, which will be at equal slope to x equal to y. So it will look like this. So anywhere over here, sigma C is greater than sigma A, and over here, sigma A is greater than sigma C. Similarly, we will draw a line here because these would define different zones where you will get different values or different forms of the same equation. Okay, so we will call this as zone 1. We'll call this as zone 2, call this as zone 3, call this as zone 4, 5, 6, 7, and 8. Now let's start from zone 1. In zone 1, what we see is that sigma c would always be greater than sigma a, and both of them would be greater than 0. So sigma c would be greater than sigma a would be greater than 0, which means that when you apply the Tresca criterion, which is maximum minus minimum principal stress is equal to the yield strength, then maximum here is sigma c and minimum is 0. Therefore, the yield strength in this one would be constant, which will be equal to sigma c. In zone 2, what we will have, okay, so before I go to zone 2, so now if sigma c is equal to y, which is a constant, therefore what we have is a form like this. So this is how the profile would look like. This is a straight line from here to here, horizontal line parallel to the x-axis. Now coming to zone 2, where we know that sigma a is greater than sigma c is greater than 0, which means this is the highest, this is the lowest. So yield strength is equal to sigma a. Therefore, y is equal to sigma a, or in fact, I should say sigma c equal to y and sigma a equal to y. So I will write it like this, because c and a are now variable while y is a constant, and therefore this becomes another straight line, and this is what we have over here. So this is a straight line. This is value is y, this value is y. Now in zone 3, what we have is that sigma a is greater than 0. Okay, sigma a is greater than 0, but sigma c is in the negative side. So sigma c, it is greater than sigma c, and therefore yield strength would be defined by this minus this, sigma a minus sigma c, or x minus y equal to constant. Therefore this will become a straight line like this, and this is what we have over here. Now in zone 4, what we have is that sigma a is also less than 0, but it is still greater than sigma c. So it is less negative than this one. Therefore, sigma a is greater than sigma c. And now in this case, what we will get is that this is the maximum, this is the minimum, and therefore 0 minus sigma c will be equal to y, implies sigma c is equal to minus y. And therefore what we get is a horizontal line. So this becomes our profile or locus for zone. Actually, this is 3 and 4, and this is zone 5. Now coming to zone 6. So here sigma c is greater than sigma a, but both of them are less than 0. Therefore, similar to this, here we will get sigma a equal to minus y. And therefore, again, we have a straight line here. This is the profile. Now in zone 8, what we have is sigma c is greater than 0, is greater than sigma a. So you can see that here sigma a is in the negative, but sigma c is in the positive. So sigma c is greater than 0, but sigma a is less than 0, and therefore the locus of yielding would be given by sigma c minus sigma a equal to y, and therefore this is a straight line like this. Therefore this becomes our hexagon type of shape is what defines the yield condition under the Tresca criterion. And here what we see is that the maximum value that any of these are taking is equal to y. So this is y, this is plus y, this is plus y, this is minus y, this is minus y. So this is a little different from the previous locus that we obtained. And again, this is for just one plane. Okay, so here we are assuming that sigma b is equal to 0. So overall, this is how the yield locus of Tresca criterion would look like in a 2-dimensional plot. So let me write it over here. in 2 dimensions while keeping third one constant, which is sigma b. And remember that sigma A, B, C also represent the principal stresses. We have not used A 1, 2, 3 because at least to begin with, we don't know which one is greater. Okay, so any of them can become greater and therefore we cannot switch the names in between. So what we have done is renamed it as A, B and C. Now, how do the yield locus for the Tresca criterion compare with that of the One Message Criterion? So if you could draw it, then what you would see is that this is how the two compare. So the red one is for the One Message and the green one is for the Tresca. So the greatest difference occurs along this line and along this line. And they are same values at 1, 2, 3, 4, 5, 6 different points, which clearly shows that both the criterions are not very far off. So both of them are very close to each other, which means both of them are fairly accurate description of yielding condition. Now let's look at one example to understand this. Let's say you are given the stress analysis of a space, one of the particular component in a spacecraft is given, and you are given that the yield strength of the material is 500 megapascal. So first let's write it. Yield strength is equal to 500 MPa. Now you are given the stress state for that component and assume that it is the same everywhere like this. So you have 100 MPa acting here in the x-axis and 50 MPa acting normal stresses along the y-axis, and there is also a shear stress of 30 MPa. So 30 MPa here and therefore 30 MPa over here. Therefore, this is a plane stress condition. Now, if we wanted to find the principal stresses over here, then we know that we can use these values and put it in the Mohr circle, and the Mohr circle, using the Mohr circle, you would know that we can get, so this will become the center of the circle, which is the x and y stresses. So divided by 2, that brings you to the center of the circle, and then you find the radius, which is equal to 100 minus 50 by 2 whole square, plus this is the shear stress 30 square. And when you calculate it, you would see that the two values would come to /megapascal. And since it is a plane stress condition, which means the third one also exists there, and therefore there is a third stress, which is 0 megapascal. So if you were to find the sigma 1 minus sigma 3, which should be equal to y for the Tresca condition to satisfy the yielding. So if you remember, sigma 1 minus sigma 3 equal to 2k equal to y. So this is our equation which defines. So if the sigma 1 minus sigma 3 is equal to y or greater than y, then yielding takes place. If it is less than y, then no yielding takes place. So we will go back and look at what is the value of sigma 1 minus sigma 3. And this is clearly much lower than yield strength. So no yielding takes place. So this is what you are asked, exhibit yielding. So no, it will not exhibit yielding. Okay, so here there was supposed to be a change. This should be equal to 300 megapascal. and similarly there should be 300 megapascal over there. So there is a compressive stress. So other conditions remain same, but additionally you are now applying a 300 megapascal stress over here. The question is, will it yield if you are applying now this additional compressive stress of minus 300 MPa? So again, what we need to do is find sigma 1, sigma 2, sigma 3. But then this time your task is easier. Why is it easier? Because sigma 1 and sigma 2, which is the plane stress condition, is already obtained. And therefore the third direction where no shear stress was acting, this will be the sigma, the other principal stress. And therefore this becomes, since it is minus, so this becomes the sigma 3. So in this particular case, sigma 1 is equal to 133 and sigma 3 is equal to minus 300, implies sigma 1 minus sigma 3 is equal to 433 megapascal. So it is still less than yield point and therefore no yielding. But now this will give you an idea that now let's say if I applied if normal stress of 400 MPa was applied. Okay, so this is less than the yield strength of the material. Okay, so on any particular axis, you are not exceeding the yield strength. Only you are applying a minus 400 MPa over here. Therefore, now this time what will happen? Sigma 1 will be equal to 133 and sigma 3 will be equal to minus 400, and therefore sigma 1 minus sigma 3 will be equal to 533 megapascal, which means that this is greater than yield strength and therefore yielding will take place. Okay, so what do we see here? That even though none of the principal stresses exceeded the yield strength of the material, but sigma 1 minus sigma 3 exceeded the yield strength, which is the highest shear stress. So as long as the highest shear stress is greater than the yield strength, then we see yielding. That is what this particular criterion, Tresca criterion, defines. And under this criterion, under this definition, we see that this will actually yield. Okay, so we have now seen two criterions, and first one was obviously valid criterion. Now, what about this Tresca criterion? Is it a valid criterion or not? So let's look at or try to determine whether this is a valid criterion or not. How do we determine? One of the things, most important thing is that when you apply a hydrostatic stress, the yielding should not change. The condition for yielding should not change. Now here we have said that sigma 1 minus sigma 3 is equal to C. This defines our yielding. Now let's make sigma 1 prime, which is a new stress. Now we have added some mean stress or hydrostatic stress to all the components. So sigma 1 prime is equal to sigma 1 plus sigma m. Sigma 2 prime is equal to sigma 2 plus sigma m. And sigma 3 prime is equal to sigma 3 plus m. Okay, so now this is the same condition, but with an additional mean stress applied on all the principal stresses, or basically on the element. And therefore, these are the new principal stresses. So now I will apply the condition onto this. So this is sigma 1 prime minus sigma 3 prime, but sigma 1 prime is equal to sigma 1 plus sigma m, and sigma 3 prime is sigma 3. So sigma 3 minus sigma m, which is equal to sigma 1 minus sigma 3. So this is same as equation 1. So this is again translates to this equation 1 and 2 are same. Meaning, what this means is that applying a hydrostatic stress did not change the yield criterion, and therefore this is a valid yield criterion. So we will do just this much test to find out whether the criterion given to us is valid or not. Okay, and we clearly see that this is valid. You can, for your exercise, you can try this also on the One Message, and I can tell you beforehand that you would find that that One Message is also a valid criterion. Now let's move on to another criterion, which is called the Rankine or max stress criterion. So one of the criterion we saw talked about maximum shear stress. So why not talk about maximum stress? Maybe we can define that. Actually, this particular criterion is not about yielding, it is about failure. But let's say it is about yielding. So yielding will occur. So let's say it defines about yielding when maximum shear, maximum principal stress at any point reaches yield strength. Okay, so to define it, this will be equal to sigma 1, because this is the maximum principal stress. Sigma 1, when sigma 1 reaches y, then yielding takes place. That is what we can write mathematically this equation into. So this is how this will be defined. But I will show you with the help of an example that this will turn out to be an invalid criterion. And that is not surprising because it is not taking into account shear stresses. It is only taking into account normal stresses. But what is more important, it is that this criterion is actually not defined for yielding, but for failure. And this is a criterion which has been found to be satisfactory for brittle materials. But not applicable to ductile materials. So when you want to talk about failure of brittle materials, then you can apply this criterion, and it has been found to be fairly satisfactory. So as is clear, one of the limitations of this model, even if you take it for failure, it does not take into account other two principal stresses. Okay, so now let's take a look at whether it is a valid. Is it a valid yield criterion? Okay, we don't know what or how to check for a failure criterion. We only know about, or we have talked about, yield criterion. So let's say you are given the stress state like this. So the material is given to you like this, and it is given that the yield strength of this material is equal to 120 megapascal. Now you are given the stress state like this, 80, 80, 40, 40. So it happens to be all principal stresses. So none of the principal stresses are equal or exceed the yield strength. Therefore, in this particular case, it is not yielding. Now let's say that we apply hydrostatic stress. Nothing should change according to our requirement for a valid criterion. Nothing should change. But let's say we are, but in this case, you would see that something would change. So let's apply sigma hydrostatic equal to minus 100 megapascal. Okay. So now what will happen is sigma 1 will become 80 minus 100 equal to minus 20. Sigma 2 equal to 40 minus 100 equal to minus 60. And sigma 3 equal to minus 30 minus 100 equal to minus 130. So now this sigma 3 in magnitude is greater than yield strength of the material, implies yielding will take place. So here what has happened, that application of application of hydrostatic stress leads to change in yielding condition. Now, this is something that we had clearly mentioned should not happen for a valid yield criterion, which means that this is not a valid yield criterion. And like I mentioned earlier, this is actually not even used as a yield criterion, it is used as a failure criterion. And over there, it has been shown or known to be satisfactory for brittle materials. Therefore, we should not use it for understanding or defining the yield condition of the material, because we can clearly see that application of hydrostatic stresses are making a difference over here. Okay, so now let's move on to one last example for the day for this particular content. Okay, so you are given a new yield criterion. Okay, remember that the yield criterions are not universal. It means that it doesn't mean that all the material will have to follow the same yield criterion. There are certain basic minimum requirements for yield criterion, and based on that, you can have several yield criterions. So one of the yield criterion is given over here. The following yield criterion has been proposed. Yielding will occur when the sum of the two largest shear stresses reaches a critical value. And if you want to state it mathematically, you can write it like this: sigma 1 minus sigma 3 plus sigma 1 minus sigma 2 is equal to C, where C is some critical value that it must reach, and it is a constant. And what we are assuming at these are the two highest shear stresses, meaning the third one, which is sigma 2 minus sigma 3, is lower than the other two. Sigma 1 minus sigma 3 has to be the highest. These two are the other two lower ones, but in these two, it is known that this one is higher than this. And therefore, this is your equation. So again, if you first thing that we want to do is check if this is a valid yield criterion. And how do we do that? Sigma 1 minus sigma 3 plus sigma 1 minus sigma 2 equal to C. Now, this is equation 1. Now, let's say we have applied hydrostatic stress Therefore, we get sigma 1 prime. This is the new principal stresses. Sigma 1 prime equal to sigma 1 plus sigma m. Sigma 2 prime equal to sigma 2 plus sigma m. And sigma 3 prime equal to sigma 3 plus sigma m. Now, what we'll do is we'll put this back into this equation. Okay, let me go one step. So now the criterion can be written as sigma 1 prime minus sigma 3 prime plus equal to C. And we will put these values from here. So sigma 1 plus sigma m minus sigma 3 minus sigma m plus sigma 1 plus sigma m minus sigma 2 minus sigma m equal to C. So these two get cancelled, and what we are left with is sigma 1 minus sigma 3 plus sigma 1 minus sigma 2 equal to C. So what we see is that this is again come down to same equation that we started with, which means that equation 1 and 2 are same. Adding the hydrostatic stress did not make any change to this equation, and therefore if the original equation defines that the material will yield, then this equation will also define that the material will yield. If it says no, then this will also say no. There will be no difference, and therefore there is no effect of hydrostatic stress, and it means that this is a valid yield criterion. Now the second part of the equation is that you have to find the value of C in terms of yield strength Y and shear strength K. Now this is something that will be useful for you to practice with various types of yield criterion. Okay, so what we do again here is we are given the equation sigma 1 minus sigma 3 plus sigma 1 minus sigma 2 is equal to C. How do we find, what did we do earlier to find the value of C? We first use uniaxial condition. What do we know about uniaxial condition? Sigma 1 should be equal to Y, sigma 2 equal to sigma 3 is equal to 0. So what we get here is that 2Y, because there is sigma 1 here, this is sigma 1 here, these two are 0. So 2Y is equal to C. So there we get the value of C in terms of Y. Similarly, we apply pure shear condition. In pure shear condition, sigma 1 is equal to plus K and sigma 3 is equal to minus K and sigma 2 is equal to 0. So we again put this here. So we have K minus K plus this part K minus 0 equal to C. Therefore, this is K plus K plus K. So this is equal to C is 3K is equal to C. So we have applied this equation on uniaxial condition and shear condition to get the values of C. And we know that this is a valid yield criterion and these are the values of C. So we have solved this problem. You can go through the book on Hosford and Cadell and you would find that there are several examples in there where you get new yield criterion. You can do the exercise of whether it is a valid yield criterion. That is simple. Just add the mean stress to all sigma 1, sigma 2, sigma 3, then put it in the equation and see whether the equation changes. If it changes, then probably you will get different values under different hydrostatic condition. If not, then it means that it does not change and therefore it is a valid yield criterion. Second, to find the value of C in terms of Y and K, just use the uniaxial condition. Uniaxial condition is sigma 1 equal to Y, sigma 2 is equal to sigma 3 is equal to 0. And then put it in the equation, you will get the value of C in terms of Y. For value of C in terms of shear strength, for the shear condition, we know that sigma 1 is equal to plus K and sigma 3 is equal to minus K and sigma 2 is equal to 0. So you put this over there and you would get the value of C in terms of K. So today in this lecture, we looked at different yield criterions. We derived the one Mises, then we looked at the Tresca condition. We also looked at a Rankine condition, which is not a yield criterion, but a failure criterion. And if we use it as a yield criterion, we saw that it will fail. It will not be valid criterion. We also looked at how to find whether a yield criterion is valid or not. And we also know now how to find the value of the constant C in terms of yield strength and shear strength K. Okay, so with that, we come to end of this topic. Thank you.